This video is a continuation from my previous video about injective, surjective and bijective functions, and I wanted to look at the different ways that injective, surjective and bijective functions can be represented. So far we've only been dealing with a sort of a toy model for the function. Now let's start thinking about functions you're more likely to meet or have already met. And predominantly, these are going to be functions that take you from the real numbers back into the real numbers. Just to remind you that this symbol here stands for the set of real numbers, and it refers to every number. That's anything that can be expressed as a fraction, and even the ones that can't, like pi or e. And there's absolutely no problem with having a function that's taking elements from one set and putting them back into the same set. Clearly, we're not going to get anywhere by drawing a set of curly brackets and trying to write down every possible number we can think of, and then drawing arrows from one set into another. We need to come up with a better way of representing what this function actually does. And one way we can do it is by introducing the idea of a real number line. So the real number line is just a line we draw on the page, and on this line lies all of the real numbers. We can put marks where the whole numbers lie, and we assume that this line is going off forever to the left and forever to the right. So along this line you could find any number you can possibly think of. So this real number line is going to be the domain of our function. We also need a real number line to represent the range of the function. And so for any point on the real number line on the left, our function is going to tell us which is the corresponding point on the real number line on the right. For example, this function is taking the real number -1 into the real number 1. So as we slide the input along the real number line, we can see that the output is sliding along the real number line, according to the action of the function. It's very difficult to get an idea of what the function's actually doing by watching these two lines slide back and forth. It's hard to keep your eye on both lines at once. So there's an absolutely brilliant idea we can use, and that is to take the real number line that is the range, rotate it so it's vertical, and place it on top of the real number line that is the domain. And now, as the input slides along the domain and the output slides along the range, suddenly we have a much better picture of what this function's actually doing. Some of you might have an idea of what I'm trying to draw here, and that's the function f of x is equal to x squared. It's taking whatever's in the inputs and squaring it. What can we ask about this function? Well, is it injective? Let's look at the number 1 in the range of this function. If we draw a line through this point, we can see that it corresponds to two different elements in the domain. F of -1 is equal to 1, and f of 1 is equal to 1. That's what we called a greedy element in the last video. An element in the range that has two corresponding elements in the domain. And so this function isn't injective. What about surjective? Well, again, you can see how the real number line extends from 0 all the way down to -infinity. And all of those negative numbers are lonely. There's no number that we can multiply by itself and get a negative number. So there's no number in the domain that corresponds to a negative number in the range. It isn't injective and it isn't surjective, so it's definitely not bijective. So what about this function? F of x is equal to x cubed. I'll draw it for you. Is this function injective? Is it surjective? And is it bijective? Have a think about it. And finally, moving on from what I think is a fantastic way of representing what a function is doing to a less fantastic way, we're going to talk about how to write down what injective and surjective means concisely. Let's start with an injective function. We say f is injective if there are two elements in the domain, x and y, that equal the same value in the range, then those two elements in the domain better themselves be equal. Because if they're different, then we have the situation where two different elements in the domain correspond to a single element in the range. And that's exactly what we're trying to avoid when we define an injective function. So to write that down again in a slightly different way, for all x and y in A, if f of x is equal to f of y, then x better be equal to y. Now I talked about the mathematical shorthand of some of these terms in my series and sequences video, and let's do the same here. Let's just translate what we've written in English into mathematical shorthand. For all x and y in the set A, if f of x equals f of y, then x equals y. This is a concise way of saying that the function is injective. If this condition is true, then the function is injective. And now, what about surjective? A surjective function means that for all elements in B, there exists a corresponding element in A, such that the function of the element in A is equal to the element in B. Do you agree that this is what we mean by surjective? That we can reach every element in B with some element in A. I'm going to leave it for you to translate into mathematical notation. If you have any questions, please ask them in the comments below, and thank you for watching the video.